All right, BC Unit 2 Day 1 assignment on the book, page 66, 7 to 27 all, 51 to 53, 59 to 60, 65 to 70. So, first problem say determine the limits by substitution, and then it says support graphically. Okay, so number 7 is a limit as x approaches negative 1/2 of 3x squared 2x minus 1. If you just plug negative 1/2 in, you get 3 times negative 1/2 squared times 2 times negative 1/2 minus 1. So we get 3 times 1/4. This is going to be negative 1. That's going to be negative 2. So that's going to be negative 3/2 using substitution. Number 8, limit as x approaches negative 4 of x plus 3 to the 1998th power. Feels like it's going to be horrible, but we plug negative 4 in, and we get negative 1. And if you raise negative 1 to an even power, you get positive 1. Okay, number 9, limit as x approaches 1 of x cubed plus 3x squared minus 2x minus 17 equals negative 1, positive 1 cubed plus 3, 1 squared minus 2 times 1 minus 17 equals 1 plus 3 minus 2 minus 17 equals 4 to negative 15. Okay. So we can put another one here. See, 10 is a limit as y goes to 2 of y squared plus 5y plus 6 over y plus 2. So first step, we're just going to plug in 2 squared plus 5 times 2 plus 6 over 2 plus 2 is going to be 4 plus 10 plus 6 over 4 equals 20 over 4 equals, did I make a mistake? Equals 5. There you go. Okay, 11, limit as y goes to negative 3 of y squared plus 4y plus 3 over y squared minus 3 equals negative 3 squared plus 4 times negative 3 plus 3 over negative 3 squared minus 3 equals 9 minus 12 plus 3 over 9 minus 3 equals negative 3 equals 0 over 6 equals 0. Limit as x approaches 1/2 of now this is the greatest integer function. Essentially, it's a function, it's like a step function, and it rounds up all the time. So you get these kind of stair-step looking function if you graph it. So if you plug this in here, it's always going to round up to the next integer. It's always going to round up. So anyways, kind of interesting. 13, limit as x approaches negative 2 of x minus 6 to the 2/3 equals negative 2 minus 6 to the 2/3 equals negative 8 to the 2/3. And when I do rational exponents, I do the denominator first and then the numerator next. So that's cube root of negative 8 is negative 2, squared is positive 4. And 14, limit as x approaches 2, the square root of x plus 3 equals, plug a 2 in, and you get the square root of 5. So these are all continuous functions, nothing weird going on. Substitution works, but that's probably going to be rare. The next chapter problem says, in exercise 15 and 18, explain why you cannot use substitution to determine the limit. Find the limit if it exists. So these ones, you're not going to be able to. So you need to explain why cannot use substitution. And then you got to try and find the answer anyways, some other way. Now, probably best bet is to just go ahead and try substitution first and see if something weird happens. So if we just plug this in, we get the square root of negative 4, which is 2i. It's imaginary, which means it's not defined. It doesn't have a real answer. So this function is not defined at x equals negative 2, so there's no limit. Like, you just can't find a limit where the graph doesn't exist, right? I mean, that'd be the answer. 16, limit as x approaches 0 of 1 over x squared. If we just go ahead and try and plug it in, 1 over 0, which is undefined. Now, it's undefined because it's blowing up, right? And it's going towards like some kind of infinity or something like that. But the function is not defined. It's a vertical asymptote. And if function isn't defined, then you can't say what the limit is necessarily there. Now, in reality, both sides of this graph would look something like this, and both sides would be going to positive infinity, but positive infinity is not a value. That's not a legitimate value to say something's equal to. Okay, 17, limit as x approaches 0, the absolute value of x over x, which is going to equal the absolute value of 0 over 0, which is going to equal 0 over 0, which is indeterminate. But the graph looks like this, so it might be good. It might be good to go ahead and look at these graphs. Okay, so we can't say, I mean, it is going to positivity, but that doesn't make sense. Now, this graph, what it does is, if x is positive, then essentially it's x over x, which is 1. If x is negative, it forces the top to be positive, the bottom still to be negative, to be negative 1. So this graph looks like this. It goes up from negative 1 to positive 1, and it jumps. And so the function is not defined at x equals 0. That's not enough to say there is a limit, but it's more that there's a jump discontinuity, right? It's okay if the function is not defined, but there's jump discontinuity. This graph right here, if you look at this graph, this is what this graph looks like. It's just not in the domain of the function. So that's why this one, it goes to positive infinity, but that's not a legitimate limit. This one has a jump discontinuity, so it has no limit because the two sides don't agree. 18, limit as x approaches 0 of 4 plus x squared minus 16 over x. If we plug 0 in, we get 4 squared minus 16 over 0, 16 minus 0 over 0 equals 0 over 0, which is not necessarily undefined. Might be a hole in the graph. What this graph looks like, I mean, if you were to clean the top up, it'd be 16 plus 8x plus x squared minus 16 over x, and these would cancel each other out, and then you could factor the x out, and this is a hole in the graph. So this time there's actually an answer. You're going to plug 0 in here, and the answer is 8. So there is an answer. Okay. Next problem, say determine the limit graphically and then confirm it algebraically. So you could use your calculator to help you do the graphical part. I'll show you on a couple of these. So limit as x approaches 1 of x minus 1 over x squared minus 1. Now, we can just do a sketch of it. Now, by the way, this is x minus 1, x plus 1, which might help you in your graph. It's going to have vertical asymptote at x equals -1, but at x minus 1, I think, as a whole. So we could do parentheses x minus 1 divided by parentheses x squared minus 1 window. We could just try that to start with. So there's a vertical asymptote -1, but not here. So this is what the graph looks like. The graph looks like this. It goes like this, and then it goes like this. And at x equals 1, there's a hole in the graph. And you could verify, well, first of all, you could verify what the value is going to. If you just go on trace, you could be like, oh, it looks like it's going to like 1, right? In fact, well, no, I'm sorry, I was looking at the wrong. As x goes to 1, looks like it's going to like maybe 0.5. So I'm thinking that looks like about 0.5. Now, if you plug value in of 1, it's going to give you blank. So you know it's a hole. Okay, so anyways, I'm saying the answer is 1/2. Now we're going to confirm it algebraically. So we're going to show work. In fact, I was already kind of on the way to that. You can take, you can factor the whole out of the graph and then plug 1 back in, and guess what you get? You get 2. So 20 limit as t goes to 2 of t squared minus 3t plus 2 over t squared minus 4. I mean, we could see it's going to be t minus 1, t minus 2. If you factor this, it's going to be t minus 2, t plus 2. So I already have an idea that at 2 there's a hole in the graph, but let's just see what this graph will be. And there should be a vertical asymptote at t equals -2. So I'm going to do parentheses x squared minus 3x plus 2 divided by x squared minus 4. Graph it. Should get a vertical asymptote at -2, but not a +2. So we're going to do a quick sketch. And it looks like the horizontal asymptote is actually at y equals 1, because the dominant terms, as you plug in large numbers, these are the dominant terms. They're the same size. The graph looks like this. And so at +2, pretty sure there's a hole in the graph. So we could go trace and kind of figure out, well, when x gets close to 2, y gets close to 0.25. And we could verify that there's a hole by doing second calc, plugging 2 in, nothing. So I think it's about 0.25. So I'm going to predict from the graph the answer is 1/4. Then I'm going to confirm it algebraically. So algebraically, since I know it's a hole now, I'm going to factor the top and bottom, and I'm going to cancel the hole out, plug 2 back in, and you're going to get 1/4. So there you go. 21 limit as x approaches 0, 5x cubed plus 8x squared over 3x to the 4th minus 16x squared. We could start looking ahead and say, well, we can factor out x squared, 5x plus 8. We could factor out x squared, 3x squared minus 16. So you know there's going to be a hole in the graph. Now this is a little funkier. Like x squared equals 16 over 3 square root plus or minus. You have two vertical asymptotes there. So we're going to do parentheses 5x to the third plus 8x squared, close parentheses, divided by parentheses 3x to the fourth minus 16x squared, close, graph it, vertical asymptote, vertical asymptote. So the graph looks like this. It looks like that, and then it blows up, and then it kind of goes through here, and then it goes like this. So at 0, I mean, it looks like there's some value here, but is there a hole there? I mean, if you plug 0 in, you do get 0 with 0, so it's, it's just probably a bad sign. So we could do trace just to kind of check it out and get closer and closer to x equals 0. And at x equals 0, there's nothing. But the y values seem to be approaching maybe negative 0.5. Negative 0.5. So I'm gonna go with that, negative 1/2. I'm gonna solve it algebraically. So you're gonna factor the top and bottom, and cancel the whole out. Plug 0 back in, and you get 8 over negative 16, which is negative 1/2. Okay, let's see. 22. Limit as x approaches 0 of 1 over 2 plus x minus 1 over 2 all over x. If you plug 0 in, you get 0 over 0. Okay. Now, when I go to do this algebraically, I'm probably going to combine this into just clean this up. So this would be the same thing as multiplying each of these by x. So that'd be 1 over 2 plus x minus 1 over 2x. And then we could, I guess there's another way. We could have combined these together, least common denominator. But I probably want to combine these together at some point, least common denominator. So you'd multiply the top of this one by 2, and the top of this one by 2 minus x, or 2 plus x, would be minus 2 minus x. And then that would give you negative x over 2x, x plus 2. Anyways, the graph of this, maybe we just try and plug in the original version of it. Parentheses 1 divided by parentheses 2 plus x, close, minus parentheses 1 divided by 2, close, all divided by x, graph, vertical asymptote. So you have one vertical asymptote at x equals 2, negative 2, which makes sense. And the graph kind of goes like that, and then it kind of goes like this. And then 0 looks like something, we can do second, no. Just do trace and say, okay, when x gets close to 0, it shows a blank, but it looks like it's going to maybe negative 1/4. I'll go with that for now. So now if I plug 0 back into here, I still get, oh shoot, should be negative x here. So then that's the hole that you can cancel out. And then if you plug 0 back in, you get negative 1 over 4. Perfect. 23. Limit as x approaches 0 of 2 plus x cubed minus 8 over x. So if we just plug 0 in, we get 0 over 0. So something's going on. So if you graph this, 2 parentheses 2 plus x closed to the third minus 8. I think I need to put parentheses around all of this. So answer it. And then divide by x and then graph it. Kind of looks like a parabola. So I guess we need a little more room here. The graph looks like a parabola. So trace what's happening as x equals 0, nothing. But it looks like it's going towards maybe 12. You know, maybe the answer is 12. So algebraically, we'd want to try and identify that hole, which is clearly a hole now. This would be, oh, it's cubed. Oh, shoot. It's going to be kind of messy. I guess I'd square it first and get 4 plus 4x plus x squared. And then you're going to multiply by 2 plus x minus 8. So then I'm going to FOIL this all out. So I'm going to get 8 plus 4x plus 8x plus 4x squared plus 2x squared plus x cubed minus 8. The minus 8 and plus 8 drop out. And then we could combine like terms. Put the x cubed first, and then 6x squared, and then 12x over x, and then we could factor out an x on the top and bottom. So it'd be x, and then it'd be x squared plus 6x plus 12, and then that's the hole in the graph. Plug 0 back in, and guess what we get? We get 12. Did good. All right. 24. So, I mean, it's a little tedious, but you guys need to be really good at this stuff. Now, I gave you guys something in the notes today to help you with this. A little bit. Now, if you plug 0 in here, you're going to get 0 over 0. Now, if we graph this, we did one very similar to this in the notes today. Sine 2x divided by x. I'm going to go back to window and just say negative 10, 10. So there's the graph. So it's like a sine curve, but it's getting less and less amplitude as you go. So it's kind of like that. And so trace at x equals 0, nothing. So there's a hole there, but it looks like it's going towards 2. So I'm going to say that the answer is 2. Now, algebraically, you're going to use this fact that the limit as x approaches 0 of sine of x over x equals 1. Okay, now this is slightly different than that, so you have to adjust it. Whatever's underneath here has to be what's in there. Now we can't pull the 2 out of the sign. We can add a 2 here as long as we multiply the top by 2. So then that's going to be 1, and the answer is 2. So 25, limit as x approaches 0 of sine x over 2x squared minus x equals 0 over 0. Now this seems potentially related to what we were just doing, right? The graph, if we graph it, let's try and graph it real quick. Sine x divided by parentheses 2x squared minus x, and then we'll graph it. Well, it has a vertical asymptote at 1/2. And then it looks like a horizontal asymptote like that. So it's kind of like this. So at 0, What's going on right there? Trace, 0, nothing, there's a hole. It's going to -1, maybe? I'm going to go with that as my guess. Now, algebraically, what we want to do is we want to use this idea from last problem, but it's a little more complicated because so I think we need to kind of break it up a little bit. So we want the sine x over x and then times 1 over 2x minus 1. And properties of limits say you could do the limit of this and the limit of this separately. So this is going to be 1 because that's that thing, right? And we plug 0 here, it's going to be -1. So it's going to be 1 times -1 equals -1. Hey, we got the right answer. 26 is the limit as x approaches 0 of x plus sine x all over x. So I might be getting a similar situation here. So parentheses x plus sine x close, divided by x, delete, graph it. And so, kind of just looks like this, right? Trace 0, nothing, but it's going towards 2. So my answer is 2. If you plug 0 in, by the way, you get 0 0. Okay, so my answer is 2 based off the graph. Now, algebraically, I'm going to split this up. I'm going to be like, all right, that's 1 plus sine x over x. You distribute the x. So that's going to be 1, and so the answer is going to be 1 plus 1 is 2. There we go. 27, limit as x approaches 0 of sine squared x over x would be 0 over 0. So we do parentheses sine x close squared divided by x, delete, graph it. So kind of looks like this, like maybe, and at 0, nothing, but it looks like it's going towards 0. So I'm going to say the answer is 0 based off my graph. Now, algebraically, I think we want to use that trick, but we want to kind of break some stuff apart. So that would be sine x over x, and that would go to 1, right? And then sine of 0 times 1 is 0 times 1 is 0. So there you go. It worked. We got a few more problems. Uh, 51 says, draw a graph of f, piecewise graphs, determine the limit as x approaches c plus and minus one-sided limit. So you have been given a piecewise function. So the first task is to graph it. So the way I graph piecewise functions, that's a line. They're both lines. So this is me. But this, we want to, our focus kind of on x equals 2. So I think I'll probably move my y-axis a little bit to the left. And so this is a line that has a y-intercept of 3 and a slope of -1, down 1 over 1, down 1 over 1, or left 1, up 1. I'm going to draw it lightly. Okay, and then the other one starts at 1, has a slope of 1/2, up 1 over 2, up 1 over 2, down 1, left 2. So this is that one. And then when you're left of 2, which is right here, we use that first line we graphed. It's an open dot. So I'm going to just darken this part of the graph. All right. And then to the right 2, we start on the other graph. It's open dot and it's an arrow to the right. So this is your piecewise graph. And then they wanted you, that was part A, and then part B was to determine the limit as x approaches c plus f of x. Now, for us, that's the limit as x approaches c is 2, which is the interesting place of this graph. And so as you approach 2 from the left and the right, it does not exist, right? Because two sides don't agree. And then you're also supposed to do the limit as x approaches c superscript. Oh, sorry, plus, I messed up. Plus is 2, right? The right side is 2. The left side looks like it's going to 1. Okay. And then part C says, does the limit exist? If so, what is it? If not, explain why. So C, the overall limit as x approaches c of f of x would be the overall limit as x approaches 2 of f of x, and we're going to say does not exist. And you could say because the two sides don't agree, because the two one-sided limits don't agree. In fact, you could write expression. You could say because the limit as x approaches 2 plus f of x does not equal the limit as x approaches 2 minus f of x, right? Or 2 does not equal 1, Or you could say that there's a jump discontinuity. So there you go. 52, c equals 2, f of x equals 3 minus x, x is less than 2, 2, x is equal to 2, x over 2, x is greater than 2. So this one has 3 pieces. Again, all kind of focus on x equals 2. So I'm going to draw my graph a little more room over here. So 2 is the interesting part. Now, 3 minus x, that'd be 1, 2, 3. Down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, up 1, left 1. So that's that first one. And the next one is x equals 2, which is a horizontal line. And the next one is that this actually looks just like the last one, I feel like, close to it, except that the y-intercept is 0 and it goes up 1 over 2, up 1 over 2, down 1. Okay, so that's that graph. So left of 2, it's the first line, opened up. Right of 2, it's the other line, opened up. At 2, it's actually, it jumps up here. There's a jump. Okay, now, that's part A. Part B says the limit as x approaches c plus of f of x equals the limit as x approaches 2 plus f of x. So from the right side, we're approaching 1. Okay. The limit as x approaches c minus of f of x equals the limit as x approaches 2 minus f of x. And on the left side, it goes to 1. So C says, what's the limit as x approaches c is a two-sided limit? Well, that's going to be the limit as x approaches 2 from both sides. They agree. The answer is 1. Even though the value of the function disagrees, that's fine. The limit exists. Both sides agree. Okay, 53, c equals 1, f of x equals 1 over x minus 1 for x is less than 1, and x cubed minus 2x plus 5 when x is greater than or equal to 1. Okay, so X equals 1 is sort of the interesting place. This is a rational function that has a vertical asymptote at x equals 1, and as x gets big as horizontal asymptote, y equals 0. When x is greater than 1, this is positive. When x is less than 1, then it is definitely negative. So that's that graph. And the other one's a cubic. I don't know, we could just plug some values in there. 0 would be 5, 1, 2, 3, 4, 5. 1 would be, negative 1 would be 4. 2 would be 8 minus 4 is 4 plus 5 is 9. So it's going to be way up here. And negative 1 would be negative 1 plus 2 is 1 plus 5 is 6. So I think it'd be over here. In the graph, it's something kind of like this. It says cubic. Now at 1, this is where things are getting, when you're less than 1, it's going to be this guy. Open dot, which actually has to be because function is not defined there. And greater than or equal 1 is going to be a solid dot, and then it's going to be the cubic. So that's the graph. So B says the limit as x approaches c plus of f of x equals the limit as x approaches 1 from the right side of f of x. So as we approach 1 from the right side, it's approaching, it looks like 4, right? And from the left side, it's actually approaching negative infinity, which is technically not an answer. You have to say does not exist. Okay? So you can't say infinity. Okay, and then so C, limit as x approaches c of f of x is going to be the limit as x approaches 1 of f of x, and it's going to be does not exist. Right away for sure. If one side doesn't exist on its own, then the whole thing's not going to exist, and the two sides don't agree clearly. So, you can say, since, the limit as x approaches 1 from the right side does not equal the limit as x approaches 1 from the left side. I mean, that's one way you could say it. Okay. Those are fun. 59 says, find the limit graphically. Use the sandwich theorem to confirm your answer. So we're going to just try and use a graph first to help us figure this out. Now, approaching 0, it seems like it's going to be 0 times 0 is 0. So this one doesn't seem so unobvious. So graph it. So there's that graph, right? And if we go trace at 0, it actually has value 0. So it's not even undefined. This isn't like a weird situation, but it is. So graphically, it looks like this. And its value is 0, so the answer is 0. Now, with sandwich theorem, we would say, oh, well, sine x is between negative 1 and 1, right? And then we multiply by x. We say, well, x sine x has to then be between negative x and positive x. And then if we, as x goes to 0, then this is going to be 0. The left side's got to be 0. The right side's got to be 0. So the whole thing has to be 0. So we'd say since limit as x goes to 0 of negative x equals the limit as x goes to 0 of positive x equals 0, then the limit as x approaches 0 of x sine x must be equal to 0. So there you go. Sandwich theorem. Okay, so the next one is going to be limit as x approaches 0 of x squared sine x. So x squared, second insert squared. That looks good. Graph it. So it looks similar, you know, some, I don't know, a little different than the last one. But it looks like it's going to 0. It's not even a hole. So the sketch is kind of like that. So using the graph, that's the answer. Sandwich theorem, we'd start with this, and we multiply by x squared. Right? And then we say as x goes to 0, this can go to 0, this can go to 0. So that's got to go to 0. So we're going to say something like, since the limit as x goes to 0 of negative x squared equals the limit as x approaches 0 of positive x squared equals 0, then the limit as x approaches 0 of x sine x must equal 0. Okay. I think for these last ones, I'm just going to show you my answers. 65 to 70. These ones says you should solve the following problems without using graphing calculator. So 65 says if the limit as you approach c from the left is 2 and the right from 2, then the overall limit is 2. Justify your answer. True definition of a limit. Both sides have to agree. 66, if the whole thing equals 2, then is that true? True or false? Yeah, here's the work. You break it up. It's true. So I'm supporting it with work. 67, 70, use the following function, piecewise function. There's a graph of it. Multiple choice. 67, what is the value limit as x approaches 1 from the left? It looks like positive 1, right? From the right, looks like 1.5. Or you can plug it into that function. The overall limit does not exist because they don't agree. What's the value of the function of 1? Well, it's going to be whichever one is a solid dot, which is that first one, which is 1. So there you go. Those are the last questions. All right.